on electrostatics. So is it fine? So we will then continue our discussion from where we had left.
Yes, sir.
Okay, good. So I will take up questions and any doubts or anything maybe a little bit later. So let me start with our discussion first, and then I will take up any questions or any doubts. So as I said in the previous class, so what we are interested in electromagnetic theory or electrodynamics is basically you need to know, let's say, these four set of Maxwell's equation. Okay, so this is I think if I do this every class, so you remember these Maxwell's equation, and you know how important these equations are. So curl of E, so I'm writing it for electric field and magnetic field. So curl of B will be equal to okay, so this set of equations, Maxwell's equation, basically captures all of electromagnetic theory. And when we talk about electrostatic, so basically we need the first equation. Okay, so del dot E, that is rho by epsilon naught. So what is rho here? Rho is the charge density, and this is nothing but your Gauss's law, which you can also write in an integral form as E dot ds, that is a closed surface integral you take. So will be equal to the total charge enclosed within that surface divided by the epsilon. So this is a consequence or a way how you can find out electric field if you know what is the charge distribution. Now, if you know the charge distribution and what kind of symmetry that exists, so you can use that symmetry to get or have a Gaussian surface. Okay, so this Gaussian surface you can create using the charge, the symmetry, the charge, the distribution has the charge distribution, depending on the symmetry of the charge distribution. So you can create a surface which is called as a Gaussian surface and use that to calculate electric field. Okay, so another aspect of the when we think of electrostatic, so in that case, curl of E is equal to 0. So this is only true for electrostatic. Okay, and this is also indicates that this is a conservative field, or which also you can write it in an integral form. This is a line integral which will be equal to 0. Okay, so so whatever in electrostatics we do, so most of the time our job is to either find out the electric field due to a charge distribution, or the potential due to a particular charge distribution, and or let's say the if we know the potential, so we can calculate the electric field. So these are the few things which we always do or need in electrostatics. So this, in a way, can be summarized in this kind of figure. So I have three quantities. So one is rho, another is my potential V, and another is electric field E. Okay, so we are trying to correlate these three quantities in electrostatics. So either one is known, one of these known, so either charge distribution is known or the potential is known. We want to find out. So if charge distribution is known, so we want to find out the potential or the electric field. So these are all interlinked through these equations that we are writing. So let's say if I know the charge distribution and I want to find out this electric field, so I will use the first equation, Maxwell's equation, and then I can find out what is the electric field due to the charge distribution. So the charge distribution here is rho, so it can be a line charge distribution. So we are talking in general. So rho, which indicates mostly a volume charge distribution, but it can be a line charge distribution or a surface charge distribution, anything. Okay. Similarly, if let's say electric field is, you know what is the electric field, so you can also calculate the charge distribution. So, and here you can also write in a integral form here, as we already saw, this E dot ds is equal to the Q enclosed by epsilon naught. That is another way of representing the same thing. Another way also, you can just simply find out, this is the most the rigorous way to find out the electric field due to a charge distribution. Okay, so this is in a vector form we are writing. So 1 by 4 pi epsilon naught. Then you take the integral over the charge density over the volume, and this represents your volume integral. Okay, and this is the most rigorous way you can find out actually. But most of the cases we want to use simpler methods or techniques, special techniques, which we can use to find out the electric field due to a charge distribution or let's say potential. So similarly, how a potential and electric field are connected. So this is simply is given by gradient of the potential. So also you can find out the potential, which is given by minus E dot dl. Okay, so this is also you can use if you know the scalar potential, so you can take the gradient of it and find out what is the electric field. So similarly, if you know the electric field, you take the line integral and find out the potential. So similarly, this rho and V, they are also related. So this is given by this relation minus rho by epsilon naught. So this is known as your Poisson's equation. Okay. And in a more rigorous form, you can also write it like rho d tau by r. Okay, so these are some of the main quantities that we encounter in electrostatics, and these differential equations or integrals can be used to calculate one of the quantities. If you know, let's say, if you know rho, you can calculate V or E. If you know V, you can also calculate rho and E and so on. Okay, so as I said, we don't use all these rigorous equations or formula that we are seeing to find out electric field due to a charge distribution. Rather, we use some techniques, special techniques or methods, which makes the problem simpler. Okay, so I will give you a couple of examples so that you can appreciate how this is the problems in electrostatic can be done in a simpler way. Okay, so let's look at one of the most classical example in electrostatic. So that is, let me take one. This is again, we are going to use all these equations that we have written down here, and we will use simply those to calculate the electric field or potential for a given charge distribution. Okay, so let me take an example. This is again, everything that I am talking about is from the book that you have. So we will start with a charge distribution, which is, let's say I have a sheet, okay, which has a positive charge distribution. And now I want to find out, so this charge distribution, this total charge is the total charge, which you can actually define as using surface charge density as well, because we are talking about a sheet of, it can be conducting or it can be insulating, doesn't matter. So we are not talking about whether it is a conductor or not. It doesn't matter. Somehow we have these charge distribution, whether it is a conductor or insulator, irrespective of that. This is the total charge. So we can define the charge, surface charge density. So this is a surface charge density, sigma. So this is typical symbol that is used. So this is Q by A, that is the area. Now we want to find out the electric field due to this charge distribution. So if you want to use the Gauss's law, so what you do is, so you now have to create a Gaussian surface, of course. And what is a Gaussian surface here? So what you use is known as, like, this is like a cylindrical surface, okay? So this is a cylindrical surface which is elongated or extended on both sides of the sheet. So you can think of it as like a paper, and on both sides of the paper, so you have a small cylinder that is extended out. So this kind of configuration is normally known as a pillbox. Okay, so this surface, this Gaussian surface that we have created is known as pillbox. So this is nothing but a cylinder. And when you now you want to use Gauss's law, which is your E dot ds over the closed surface, that is Q enclosed by epsilon naught. So this is what we want to use. When you want to take the integral E dot ds, so now we have a defined surface. But if you look at, and what is the electric field due to this charge distribution? So you know, if it is a positive charge, so the electric field will be always going away from this positive charge distribution. So the electric field will be always in this direction, okay? So this is the direction of the electric field. So similarly on the other side, so the direction will be towards this. So this is your electric field direction. So this electric field, if you imagine a little bit, so you can realize that this electric field is always perpendicular to the curved surface. So since we need to take the integral over the surface, so a cylinder has a circular surface. So here you have some surface on both ends, and then you have a curved surface uh, depending on the distance. So you can define, let's say this is the distance r, which is extended the same in the both sides. So this is the distance r. And what you will realize, on the curved surface of the cylinder, electric field is always perpendicular to the surface. So this E field is always perpendicular to the curved surface. Okay. And it is parallel to the circular surface, or which are the ends, which are at the ends. So now if I want to calculate what is or apply Gauss's law, so it is basically, so E dot ds, so it is a double integral over the surface, which I will write as E dot ds over the curved surface plus E dot ds over the circular. Now, since this electric field is always perpendicular to this surface, so which is the area vector that we are defining, so this E dot ds will be always 0. So the first term will be always 0, and what we are left with is the second term only, and the second term is nothing but E dot. So simply this is a scalar product, which will be just simply E into the magnitude into the surface on both sides. Okay, so we have two surfaces here. So one surface here and the second surface on this cylinder, and electric field is always so parallel to the surface, and so we will get this left hand side of the Gauss's law 2Es, and the right hand side, as per Gauss's law, it is again Q enclosed divided by epsilon. So the electric field then will be equal to simply Q enclosed divided by 2 epsilon naught S. Okay. So here, what is nicer to do is, instead of writing it in terms of the total enclosed charge, so what you do is you write it in terms of the surface charge density. The surface charge density, as we defined earlier. So here, since we are talking about the surface as S, so this is the surface area. So this is sigma by S, and the electric field will be therefore so sigma by 2 epsilon. So this is a very simple formula that we obtained for a sheet with a uniform charge distribution. And one thing which we need to assume here, that wherever, so we want to find out the electric field at any point in the space which is far away from this charge distribution, and we assume that this charge distribution is uniform and it is like infinitely large, and also the thickness is very small, it is very thin or very narrow sheet. So how thin it should be? So it should be thin enough so that the distance r where we want to find out the electric field is much larger than this thickness. Okay, so you can neglect the thickness when you compare to the distance at which you are calculating the electric field. So this thing exactly we can extend to a two sheets or two plates. Okay, so instead of taking just simply one sheet, so you can take two sheets of charge distribution, and one can be, let's say, positive, and the other can be a negative charge. So this can be sigma 1, the charge surface charge density. This is sigma 2, and this basically gives rise to the concept similar to the concept that you are familiar with, which is the capacitor. Okay. So here we have to be exclusively say this is a conducting plate. So you take a conducting plate. So now you can calculate what will be the electric field outside the plate, what is it is inside the plate, and what is the electric field outside. So you can calculate. So because now there will be contribution from both the sheets or both the plates. So there will be, let's say, we can say due to the positive charges, it will be sigma 1 divided by 2 epsilon naught, and for negative charges, it will be sigma 1 divided sigma 2 divided by 2 epsilon. Okay. So this is, then you can add up and subtract, and you can find out what will be the net electric field within and outside. So this is, we are using a Gauss's law to find out the electric field, very similar to a capacitor kind of situation. So one thing which also you will notice that the electric field that we are defining is independent of the distance that we are talking about. So anywhere, due to one of the sheets, it is everywhere it is the same. So this is also interesting. Okay, so it does not depend on the distance r. Although we started with, we are saying what will be the electric field at a distance r, but irrespective of any point you think of, so everywhere it is the same. So that is also interesting, and it only depends on the charge density or the surface charge density. So the same problem, although we only know what is the electric field. Okay, so this you can also extend into other geometries. So you can extend it to a spherical geometry or cylindrical geometry. So you can find out what is the capacitance or this electric field. If you take two cylinders, okay, or you can take a spherical surface, and you can say what is the charge distribution on the surface and how the electric field will vary inside and outside. So these are some of the problems already you can do from the book itself. But what I want to now move on to the similar problem, but we will use a different technique, which is based on your Poisson's equation and Laplace's equation. Okay, so we will use this another technique, the same problem we have, but also we can obtain a similar, exactly the same result that you have seen here. Okay, so this is what the beauty of this electrostatic is, and different approaches that you can take to obtain a solution or to find a solution or finding electric field due to a charge distribution. So so the Poisson's equation is del square V is equal to minus rho by epsilon naught. Okay, so what is del square here? So del square is again an operator. It is a scalar operator. So del, this is a vector operator. So you have to be very careful about these operators. Okay, so many times people get confused. So you better pay attention to that. So this is a scalar operator. So scalar operator means it can only operate on a scalar function. Okay, So del square can never operate on electric field or any vector. So del square will always operate on a. Of course, there are also situations where it may operate on vector field, but uh, for to keep things simpler, so we say del square is a scalar operator and which operates on scalar field, or let's say scalar function. So in a one dimension form, so del square will be d square by dx square. But if you want to write it again in 3 dimension, so del square would be equal to del square. So partial derivative with respect to x, y, and z. So this will also have a different form if we talk about a spherical polar coordinate or a cylindrical coordinate. So the form will change. Okay, so but I want to this is your Poisson's equation, and you can also write this equation del square v is equal to 0, which is your Laplace equation. So which most of the time we solve this kind of equations actually in electrostatics, because the potential is a scalar function, so that is easy to calculate. And once you know what is the potential, so you can take this partial derivative, and eventually if you know what is the potential, so you can then calculate electric field and so on. Okay, so in the second unit, you will see most of the things that is related to your mathematical physics. I think you will be doing that. But this is just an application of those mathematical methods that you learn, or techniques that you learn, we will be using here. But what we will do now is look at a similar charge distribution that we talked about. Okay, so capacitor kind of thing, and try to find out how we can solve for it. Okay, so again, so I have a situation. I have, let's say, so here I can take, let's say, minus on this axis. Okay, so negative charges, and this I have on this plate I have positive charges, like the problem we had earlier. And we define, so this plate is at now x equal to 0. This is x equal to d, so this is my x-axis. And I say the potential V is 0 on this plate, and I have a finite potential V naught on this plate. So that this gives rise to a potential difference of V naught between your negative and positive terminals or your plates. And we will use now what we want is find out first, solve for the potential, because we are going to use the Poisson's or Laplace's equation here. Why we want to, or we will use the Laplace's equation here, because we want to find out the potential here, the potential here, okay, and what is the potential here due to this charge distribution. Okay, and within, so since the region, there is no free charge within this region, so we will be using the Laplace's equation instead of Poisson's equation. Okay, and you can see these equations are nothing but some differential equations. And in physics, whenever we want to solve any differential equation, so you need to use a boundary condition. Whether it is you talk about quantum mechanics or here electrostatic, electrodynamics, we always, to solve this differential equation, so you need a boundary condition. And what is the boundary condition here? So we already defined that boundary condition, that when x is equal to 0, v is 0, and when x is equal to d, v is d naught. Okay. And we are trying to solve this differential equation del square v equal to 0. But as we can see, the potential only varies along the x direction. So since we are here considering as a infinitely large charge distribution in y and z, so the potential variation in y and z will be very small, so almost negligible. And so for practical purposes, we can say this equation we can just simply write as a one-dimensional differential equation. D square v by dx square will be equal to 0. So in that case, simply we will get, so dv by dx has to be a constant, and v will be equal to cx plus d. So that's simple, the integration we have performed here, and this is what we have obtained for v. And now we will apply the boundary conditions so that we can find what these C and D are. Okay, so C and D are these are arbitrary constants and numbers. Okay, so we don't know what they are actually. Now, if I put x equal to 0, so I know v is 0, and that means d will be equal to 0. Okay, so simply I am just substituting what the boundary conditions I'm using here. So x equal to d, so I have v will be not 0, so it will be v naught. So it is v naught, which is equal to c into d. So that means my C. So here, the C is not the capacitance we are talking about. It is just this constant term that we want to find out. So it is V0 by D. So therefore, my V, so I now know D will be 0, C will be this form. So V, now I can write as V0 D by X, simply that, so because D is 0. So that means my potential varies as a function of x, of course. So at d equal to x equal to d, it will be v0. At x equal to 0, it will be 0. So satisfies the boundary condition. And this is how the potential will vary as a function of x. Now, what will be the charge density or electric field first? What will be the electric field? So this is, again, we say gradient of V. So since we are talking about a one-dimensional problem here, so it is simply minus dB by dx I cap. So this is the x-axis. We are sticking to one-dimensional problem. So now if I take the derivative first, derivative of V, so I'll be simply have minus V0 by d I cap. So this is the electric field between these two plates. Okay, so this is the electric field V0 by d minus V0 by d. Now we can use again Gauss's law to find out what is the charge distribution sigma. Okay, which if you do a little bit of the integration form, so you can write it simply as epsilon into E dot n cap. So what is n cap here? So n cap is a unit vector perpendicular to the surface. Okay, it is an so this E dot n cap is nothing but it is the normal component of electric field along the perpendicular to the surface. And since we know what is the electric field, so this is minus V0 by d, and the perpendicular n cap here will be again simply I cap. Okay. and your sigma will be equal to epsilon naught V0 divided by D. So depending on which surface, so the unit vector can be plus I or minus I. So, but the magnitude of your surface charge density will be given by epsilon naught V naught by D. And from here, you can then calculate what is the total charge. The total charge will be so sigma into this area, okay, so or sigma into A, which will be equal to epsilon naught V naught A divided by D. And from here, so we can define the parameter that is your capacitance C, which is your Q divided by V0, so which you get this formula epsilon naught A by D. So this is the capacitance of this parallel plate capacitor, which you can obtain using the by solving the Laplace equation. Okay, so which basically we use or like from intermediate or school physics we everyone knows. This so here using this Laplace's equation, so we are able to find the potential, the electric field, and even we have gone further to find out the parameter, the capacitance, which is a kind of tells you how much charge this parallel plate can store for a given potential, and for for a given potential, how much charge it can store. Okay, so this is the capacitance basically. So this is another technique or tool that we can use to find out or solve electrostatic problems. Okay, there is another technique also. So now you can solve similar examples also from the book, and I would encourage that you solve this example number example 2.5. Okay, so this is an interesting example. So try to solve that and try to understand that. This is interesting from the point of view because it is a direct application of electrostatic in semiconductors. So nowadays, as you know, so semiconductor is, it's an important material for many of all of our devices, electronic devices. So this is a nice example which shows how electrostatics can be useful to understand even semiconductors, basics of semiconductors, and particularly this is about a PN junction. Okay, so which is a basic semiconductor device. So please try to look at that problem. I will now look at another technique, which is again a technique to find out the electric field or the potential for a given charge distribution, which is known as method of images. Okay. So again, we will take an example and then the things will be much more clearer before just showing you with all the formula or anything. So what we have is like a problem. We have a conductor, let's say, okay. So we say it is grounded. So this is grounded means there are no charges. So, and I have a positive charge Q here, and I want to find out the potential V due to this charge Q in presence of a conductor, so which is at a distance, let's say this is at a distance T. Okay, so what is the potential above the conductor, so above in this region. So we want to find out the potential anywhere in this region due to this kind of situation. So we have positive charge Q, and we have a conductor which is grounded. So this is V will be equal to 0 here, which is also known as a equipotential surface. The similar equipotential surface you also see in case of a surface of a conductor. So if I just simply take a conductor, okay, and I have a surface charges, so basically the electric field will be 0 inside, and so I have all the charges will reside on the surface depending on what is the charge outside. It can be positive or negative charge, but this surface is also a equipotential surface. Okay. So we have basically a conductor which is a flat sheet kind of thing now, and we want to find what is the potential due to this situation. Okay, so now if there is no conductor, let's say, okay, so there is no conductor, so what will be the potential? So without conductor, the potential will be simply, so due to the charge, simply will be equal to 1 by 4 pi epsilon naught Q by R. Okay, so this is a simple, so I have one charge Q, and the potential due to that charge will be 1 by 4 pi epsilon naught by R. But if I keep a conductor which is grounded, so what would happen? Immediately I will have induced charges. Okay, so I will have induced charges on the surface. And that means now the situation is different and the potential will be different, because the potential has to take into account how much charge is induced on the surface. But we don't know how this charge distribution is on the conducting surface, because Q, which is at a distance d, so this does not tell me how the charge distribution on the conductor will be. It only tells there will be a surface charges that will be induced on the conductor, and that is going to affect my potential V. So this is, again, you can think, okay, I can solve, let's say, Poisson's equation or maybe a Laplace's equation, okay, and try to solve the differential equation. But that is very tedious, okay. So there is another way, which actually is, I would say, found is luckily, okay, but it works really wonderfully, works well. So what you do instead of solving this particular problem, so okay, so let's, I mean, in order to solve the Laplace's equation, for example, so you need to know what is the boundary condition. Okay, so what is the boundary condition here? So at least one we know already. So V equal to 0. So we can say this sheet is extended on XY plane. This is my XY plane. Okay, and this is my Z axis. So which is along this, so this is my Z axis. So that means when Z is equal to 0, V is 0. This is the grounded conductor, so V is equal to 0, equipotential everywhere, potential will be 0. And also what I can say that V will tend to 0, it is not exactly 0, but it will be tend to 0 when this distance, which is equal to R square, is much greater than D square. So D, what is D here? D is the distance of the charge. So if I am going to very like infinitely further from this charge distribution, so I expect the potential will be 10 to 0. So it will get smaller and smaller always. So because of this 1 by R dependence. So it will be smaller and smaller, but it will be eventually be zero at infinity. But if this value is much greater than d square, in that case also we can say v tends to 0. So this is the boundary condition, and on that basis, so probably we will start solving the differential equation and find out. But let's look at completely a different problem. Okay, so I have, again, I'm just defining the axis here for the convenience. So I have this x, y, and z plane, and I am taking so this q I have placed at a distance d. Now I put another charge minus q at distance d below this origin. So basically this is plus d z positive z direction, and I take a minus q, which is in the negative z direction, and I want to find out what is the potential due to this charge distribution at due to at point P. Okay, so what is the potential at point P? What is V? Okay, so this is what I want to find out for this charge distribution. Okay, so here I can say this distance will be, let's say, R1, and this say R1, this is R2. Okay, and what will be R1? So this is the coordinate here is 0, 0, D. This minus q has a coordinate 0, 0, minus g. Okay. So in that case, the potential due to the charge distribution, so simply will be, so q by 4 pi epsilon naught r1 and minus q by 4 pi epsilon naught r. So the charges are same but opposite. So one is q by 4 pi epsilon naught, the distance r1, and the other one is minus q by 4 pi epsilon naught r. So I can write down the form of R1 and R2 in terms of x, y, z, and d. So just using the your vector addition, so you can find out the R1 will be simply x square plus y square plus z minus d whole square, and R2 square will be equal to x square plus y square plus z plus d. So this is your R1 and R2, and you can just substitute in place of R1 and R2 these expressions, and you can calculate what is V. And now let's see what will be the potential when Z is 0 and when we go far away from this point. Okay. So if Z is equal to 0, okay, so R1 would be equal to, so this is the square root. So Z is 0, so it will be x square plus y square plus d square, and R2 is also equal to x square plus y square plus d square. So that means this potential V, which is now it is a Q, so charge is same, the denominator is also same because R1 is equal to R2, R1 is equal to R2, so this is same as R1. So at Z equal to 0, V is equal to 0. Okay. So now what is the situation when we are far away from this charge distribution? So far away means we are saying x square plus y square plus z square is much greater than d square. So in that case, you just take so this whole term will be again will go to 0. Okay, so we will tend to 0 because you can take this z out, so it will be sorry, d out, and it will be z by d square, which you can neglect, and then it will be simply x square plus y square plus z square, and so it will be going to 0 as you go farther away from this charge distribution. And when you look at the boundary conditions, so this is our boundary conditions that we have obtained for such a charge distribution. And now compare this boundary condition with this problem. So we started with the problem where we have a positive charge Q close to a conductor which is grounded, and we want to find out what is the potential. And in that case, we said that the boundary condition is V will be 0 or Z equal to 0, and V should tend to 0 when x square plus y square plus z square is much greater than d square. And the same boundary condition we get for this kind of charge distribution. So without any conductor, so this is again a imaginary situation that we are talking about. So we have a positive charge Q and negative charge minus Q, which is at a distance d from the origin both. And they also have exactly the same boundary conditions. So they satisfy both the boundary conditions, exactly the similar boundary conditions. So this actually is useful, and we take a help from something known as a uniqueness theorem. Okay, so which tells us if the boundary conditions are the same and we are trying to find out the potential, so solve the same differential equation. So if the boundary conditions are same, so according to uniqueness theorem, so the whatever solution we have found, so it is for potential, it is always unique. So there will be no other solution possible for a particular charge distribution. Okay, so if the boundary conditions are the same, so the solution for potential has to be same. Okay, so this is the essence of uniqueness theorem, which we can use now and tell and say that the problem that we have defined or started with, this problem of positive charge Q with a conductor, grounded conductor, is equivalent to a problem where we have a charge Q and another charge minus Q separated by the same distance. So this minus Q is known as an image charge. So what we have created is an image charge, which is not a real charge. It is not a real charge. Just like a virtual image that you have create, but you see yourself in the mirror. So it is not a real charge. But this kind of situation exactly describes or hits the boundary condition of the problem that we started with. And that's why, and if we use the uniqueness theorem, so the potential, the solution that we got here, V, should be the same for the other problem as well, because they have the same boundary condition. So this is the nice thing about uniqueness theorem. So because of uniqueness theorem, we can say that. And that's why this problem that we started with charge Q and the conductor, the potential will be simply Q by 4 pi epsilon naught R1 minus Q by 4 pi epsilon naught R2. Simply that. And this method that we call as a method of images has made the life simpler, because we don't need to really solve the differential equations. Okay, so it can be tedious actually in this case. And one thing which I should emphasize here, so this solution is possible only if we want to find what is the V in this above the conductor. So if we want to find what is V in these regions, so then this method of images does not work. So method of images is a special technique, but only applicable for certain cases. Okay, so very few cases where it is applicable, but it has its own advantages, where you can basically change the problem and define a new problem where you come up with a image charge of your charge q, and you just ignore the existence of conductor at all, and you just say, okay, I have a image charge minus q, which is simply a distance d from this place, so they're equidistant, and the potential due to that will be the same. Okay, so this is the power of method of images. You can use it for spherical cases, but again, what will be the value of charge q? It may not be always. So here in this case, this is a simpler case. So this is why plus q and minus q both have the same magnitude. So it might be possible the magnitude can be different. So for different charge distribution, uh, and where this charge has to be located can be different also. So that's why it is not applicable in many cases. Okay, so only few cases this method of images is applicable. Okay, so basically I wanted to show different techniques or methods. So we started with Gauss's law, with the example of parallel plate capacitor kind of thing. Then we used a Laplace's equation, so solving differential equation. So where we can understand what will be the electric field and the potential due to a particular charge distribution, again in a parallel plate kind of situation, solving Laplace's equation, differential equation. So, and the third thing what we did is we created a completely new problem out of the existing problem and use uniqueness theorem, okay, so that we can say, using this uniqueness theorem, we can simplify the problem and find out the potential due to a particular charge distribution. Okay, so these are some of the techniques which, again, are just to summarize what has been done in this course. So if you have right now any questions, so I will take it up before moving further. So if you have any.
Sir, please,
Yes.
sir, please elaborate again in which cases a method of images can be used and in which cases method of images cannot be used. How to differentiate?
Method of images. So you can, I mean, in principle, you can use in all situations, okay, all problems. But the question is how to find that exact charge or the charge distribution. Okay, so let me draw this problem side by side. Okay, so we said this is my conductor, grounded. This is my charge q. Okay, so which is at a distance d, and I am saying this is equivalent to a problem where I have a charge q here at a distance d, and this is a minus q, which is again the same distance. Okay, and the potential at point P in both these situations are exactly the same. Okay, so this is what the method of images tells me. But if I want to find, let's say, a potential at a point P prime here, I cannot use this. Why? Because the when I am creating the method of or using method of images, so it is on the other side. So it is so method of images, when I'm using it, it is everything, the virtual charge that I have created is below this conductor. Okay, so it is outside the region where I want to find out the potential. So I want to find out the potential in this region, okay, or anywhere here. So that's why if I create a minus q charge here, like I have created here. So this is fine. This is acceptable. This is not going to affect anything. But if I want to find now the potential in this region, so I cannot use this method of images. Okay, so this is the constraint I have.
Okay,
So
sir. Thank you.
similarly, huh?
Okay, sir. Okay, sir.
Yeah, another thing is if I take, let's say, sorry, a sphere. Okay, so again, I can put it, this is a conductor, okay, so which is grounded, and I have charge Q here. Now, the question is where I should create the, so I want to find out the potential at point P, so which is outside the conductor, okay, fine. So I can create a image charge somewhere within the sphere, of course, but where and what should be the charge? It may not be exactly minus Q, okay? So this is not minus Q in this case. It will have a different value. So similarly, where I should place this minus Q so that the potential due to this configuration plus Q and conductor is equivalent to a so this is my origin, let's say. This is distance D. Okay, so this is my charge Q. So Q will be placed at some distance D. Okay, so what is this distance? I don't know. I have to find it out. So this is all not trivial for most of the problems. Okay, of course, this has been solved for this the example that I'm showing here. But again, if you go to a cylindrical system or maybe other kind of distribution, so it is not that easy. Okay, so this is the limitations. Okay.
Okay, sir.
Okay. Any other question? So I will post, I have created another Google Classroom, so if you can quickly try to I will put the link here in the chat box. So can you join? Can you try, some of you, if you can join this Google Classroom? Whether it works.
So that day it happened, means we were able to join in that classroom
You
after
could?
meeting Google Meet.
Okay. Okay. Oh, I didn't check. So I can check that Google Classroom again. Just to see. I mean, everyone joined or only few joined? See, where is that? Okay. The Google Classroom. So then
सर
just
हमारा ज्वाइन नहीं हुआ
नहीं
बाद
हो
में भी,
सबका नहीं हो रहा है
पर इस वाले में हो गया,
इसमें आई थिंक हाँ इसमें शायद हो
इस
जाएगा
वाले में
सबका
हुआ अभी।
कितने टोटल स्टूडेंट कितने हैं क्लास में एनी आइडिया
So 47.
टोटल 47 so then इसी में हो जाएगा प्लीज जॉइन दिस क्लासरूम
Sir, we are attending 47 here today, but total enrolled student is more than 300 if you consider both the batches. Okay.
okay. I didn't know that. Okay, anyway, I think if some of you can join here, so whatever material I will post, it will be in the form of a PDF, so you can share it within your groups. I'm pretty sure you must be having different WhatsApp groups, so you can just share that material.
So that
Sir,
will be very helpful.
Newman and Dirichlet conditions are part of uniqueness theorem or they are different?
Oh, they are part of the uniqueness theorem. So these are the boundary conditions. Okay, so different boundary conditions. Basically, it is part of the uniqueness theorem.
Installation of Google charges. It is asking 100 rupees per month. Is it so?
Okay. So it is asking for money. So not free. Okay. or okay, if, those
No,
who
no,
can
basic
join.
features are free, sir. Only if you want to have premium features, then only it is charging.
Yes. So for basic features, it is free. Yes. So if one wants to do like conduct quizzes or assignment and those grading kind of thing, it will be chargeable. Otherwise, just to join and post materials, it is free. Yeah, I think I see 7 students already joined. So it is fine if some of you join. What is essential that I just post some of the like whatever I'm doing in the class, this teaching notes, so that you can go through that.
Now it's a 24, sir.
Hmm?
Now it's a 24 students join.
24. Okay. Yeah. Okay, I will post these materials there, so it will be helpful. Okay, any other question you have before we start?
सर
Yes,
हमें अपना ऑफलाइन किताब कब तक मिल जाएगा मटेरियल्स
offline. That I think you have to ask the coordinator. So I cannot answer that. जो ऑफलाइन नोट मतलब कौन सा नोट, कौन सी नोट की बात कर रहे हैं?
मटेरियल्स जो आते थे
Which one?
Book, book.
मटेरियल
Book.
हाँ बुक्स हाँ
Books. ये मुझे पता नहीं, कोऑर्डिनेटर ही बता पाएंगे. Okay, so I will try to find out if I have access. I will share it. Even I don't have access to this book on electrodynamics. So I have only the book from electromagnetic, this MPH-3. So MPH-7 or 007, I also need to get the study material for that. So I thought if some of you have that material, maybe you can share it with me.
Mm. No, sir, we have all the material in soft copies. It's available in IGNOU. We have PDF. What ma'am is asking is when we will get the book, and that only IGNOU can tell. And they make so much late in
Okay.
sending the books.
Okay, yeah. I mean, this. I think whatever book you have, the soft copy is good enough. Like if you solve those questions, our examples, solve the examples and also the questions, because solutions are also given. So solve that. That is good enough. Okay. Or for
Okay,
this
sir.
course, that is good enough.
MPH 003 will be of 50 marks or 100 marks. Sir, do you have any idea?
You are all asking difficult questions. Which only the coordinator of the can answer. Okay.
It will be means what I predict it will be 50 marks because it has 2 credits and the time given is 1.5 hour because within 3 hours you have to attend 2 papers, electromagnetic theory as well as classical mechanics, 100 marks.
Okay.
That's why it will be 1.5 hour time and 50 marks
Yeah, I
question.
also think so. Yeah, I also think so.
Okay. Okay. Yeah, I think don't worry
Sir,
too much
please,
about the
please
exam.
suggest.
I think everyone will pass. Don't worry.
Sir, if you suggest a book, means other than our book, because
Yes.
book will come, offline book will come, so we can get a book which has a little bit of explanation, I mean, easy to self-study. Can you suggest any book?
So last time I suggested this
Yeah,
Griffith.
Griffith.
If you want Yes, yes.
Griffith is not having the derivations. I was seeing Griffith. It has means
Ah,
it has skipped so much steps. Means
yes,
it's a
yes.
little bit compact
No,
book.
it
I
is
saw.
more like look point. So Griffith is so some steps are there more on physics. So it explains more of the physics, not
Yes.
the equations, how to solve and how to derive. Okay. Uh, for simpler one, I mean I don't know about any Indian author which I can refer to.
You means sir, please suggest us where we can do self study. Actually, we are
Mhm.
means not getting enough classes and the
Yeah.
books are less, na. So we need a book where things are a little bit explained from the introductory level, so we can
Mhm.
do self study actually.
Mhm.
Means,
I
Correct, sir.
understand.
We want some similar books because
Mhm.
they are doing very late.
Yeah. No, I understand. So I will find out maybe today or tomorrow. I will suggest. Huh? So for
Okay,
electrodynamics,
sir.
what will
Okay.
be a better book, which will be simpler and uh,
And sir, MPH-7,
uh-huh.
that is electromagnetic is the two second part.
Yes,
That also covered in Griffith only,
everything
or
is
it
yes,
will.
yes. It is in Griffith. Yes,
Okay.
everything is in
So
Griffith. Yes,
Griffith will cover two papers, no?
yes.
Okay.
Actually,
Okay.
the study material there is many steps are jumped, so it becomes
Ah,
sometimes difficult to understand the perspective as a whole.
okay.
So now you are there, we are getting better shape, but still,
Yeah.
uh,
So what I suggest, let's say, let me just complete this electromagnetic theory part. Hmm?
yes, sir.
I mean, unfortunately, as you know, so this course, this is typically like a 14 or 20 lecture course, no, not 2 hours or 4 hours lecture course. So we have to uh, rush through many of the things. I am also rushing through many of the things. But what we can do is, let's say, so tomorrow we have a class, and then day after tomorrow you can so you do a little bit of study and then come up with like these are the steps in between steps which we did not understand. Okay, these are the things which we missed or needs more explanation. So you can tell me and I will fill those gaps. Okay, so that way, yours once you have completed a kind of a self-study, so you know, okay, these are the things which I do not understand, and sir, I need help here. So can you please elaborate here? So that way,
Ac-
it will be much more effective.
Actually, there are two parts: physical
Hmm.
science and mathematical interpretations. In
Hmm.
the courseware, the mathematical, I mean, explanation is quite missing, and I mean that's why it creates some problem. Unless I understand the whole perspective, it is
Hmm.
difficult to retain as a whole. When the professors are there who are
Hmm.
explaining the things, it is easier
Hmm.
to get the thing fine. But
Okay.
it is so fast and volume.
Yes.
It is so voluminous. The
Yeah.
moment we try to retain it, become difficult, and we
Hmm.
lost the track. That is
Yes.
my take anyway. Hmm.
No, that is
Thank you.
true. I agree. I agree. Yeah.
Sir, another request, you
Yes.
can means it will be difficult for you, but you can prepare notes for us, or it's
uh,
you
think
can author a book also.
yeah, no. I mean, there are many books already available, so there is no need for me to write anything. I will suggest some books. Okay, so don't worry. I will tell you. I'll post it in the Google Classroom by today night, so that you know which books you can read.
Okay.
We
Okay, so
don't have
let's.
any. We
Yes.
don't have any even a month for our exams.
Hmm.
When will we prepare?
Don't worry. So questions will be similar to what you will be solving in the terminal questions. No, so don't worry.
Actually,
Uh,
actually, this is not the way we should learn physics. Okay, physics is
I,
very critical subject as well, and it should be respected. Actually, course was designed fantastic. No issue of that.
Exactly. Yeah, yeah,
But
yeah, yeah.
but the thing is, it is, I mean, the student preparation of study material distributions to the students, and more so this counseling class might
Hmm.
be, if you have this 4 5 months back, it would have been easier for us to understand the whole thing. So we thought
You know,
this
I
bit हो रहा है,
mean, just to
लेकिन देर
interrupt.
हुआ ठीक है, might be next semester में better हो जाएगा, ठीक है, I
Yeah, yeah.
understand.
So just to interrupt here, so I am not
Sure,
the
sir.
person who decides all these
Absolutely,
things. Okay.
absolutely,
So
absolutely.
you are complaining at the wrong
Now I'm not
forum.
complaining. That's I'm sharing my viewpoint.
No, no,
That's
I
it.
understand. I understand that. But unfortunately, I don't have any control what to do, when to do, how to do, right? So I just was given or requested that can you take these many classes? So I said I will try and see how I can do. So that's what I'm trying to do. But yeah, uh, so we have to complete, let's say, whatever has been asked us to do that. Okay.
Okay, sir, we'll continue.
Yeah. So let's continue. Then I want to touch upon another aspect of this electrostatic before going to magnetostatics. So when you so far, like most of the things when we discuss in electrostatics, mostly we talk about conductors. Okay. So and in a conductor, as you know, so conductor. If I take a conductor. Okay, so simply I am drawing this spherical system because that is what you will find in most of the books. So you will see this is so the electric field is always perpendicular to the surface. Okay, so this is perpendicular to the surface of a conductor. So electric field will be zero inside the conductor. So that means, and why it happens? Because you have so conductor means there are lots of free charges available, and whenever you apply any electric field, so there are so many free charges available, so they just can move around and rearrange themselves so that they don't allow the electric field, external electric field, to penetrate into the conductor. Okay, so this is the nice thing or nature of a conductor, because you have lots of free charges, which are basically your free electrons, which are responsible for the conductivity of the material, high conductivity of the material. So that's why they will just rearrange and make sure that the electric field does not penetrate into the conductor. But all the materials are not have this unique characteristic. So there are lots of materials which are insulating in nature. Okay. So insulating means they don't have any this free mobile charges. So the charges, they of course have atoms, and they are, of course, have positive charges, nucleus, electrons, but they are not mobile. Okay, so they are not as free as the electrons, for example, in conductors. Okay, so they will behave a little bit differently when you apply a electric field. And this is where the concept of polarization, dipole, electric dipole moment, all these concepts arise. So in the context of insulating materials, or normally what also they are referred to as dielectrics. So how they behave to external electric field is very different compared to that of your conductors. So dielectrics have so no mobile or free charges. Now, when you are so what is the implication of a dielectric, which you might be knowing that when we talk in terms of a capacitance, so we said it is simply epsilon naught A by D. So this is the parallel plate capacitor that you know from your 12th and many other even in undergraduate. And so this is the positive and negative. So let's say this is the capacitance of this capacitor epsilon naught A by D. Now, if I introduce a dielectric, so what I know that the capacitance will increase. Okay, so this is so if I introduce a dielectric within these two parallel plates, so immediately the capacitance increases, and let's see what is the reason for that. Okay, so I can take, let's say, so I'm now drawing it in a horizontal direction. Okay, so I have these negative charges here. These are on the conductor. So these are all free charges. Now I have introduced a dielectric within this capacitor. Okay, so this is my dielectric. And so which is, let's say this distance is D. Now let's calculate the electric field due to this within the capacitor due to the dielectric. Okay, so we did this problem earlier without any dielectrics, and we found out what is the capacitance will be. So let's do that with a dielectric. So again, we will be using the Gauss's law. Okay, so what is the Q enclosed divided by epsilon naught? And but what will be the Gaussian surface that we are going to choose? So the Gaussian surface that we will choose is, it is a part of the conductor and part of the dielectric. Okay, so this is the Gaussian surface, let's say we choose, and use this Gaussian surface to calculate what will be the electric field and what will be the charge enclosed within. So the electric field, so the capacitor, what we have done is we have applied a certain the voltage. Okay, so this is why we have got a positive and negative charges on the plates. Okay, so we have certain potential on the plates. Now, due to these negative, let's say if we look at the negative, since we are looking at the negative surface, so if we have the negative side of the conductor, so what it will do in the dielectric, it will induce some positive charges on this dielectric side. Okay, because these are all immobile charges, so it will induce some positive charges, and then, but since the total charge of the dielectric has to be neutral. Okay, so you cannot have a positive charge, only a positive charge on the dielectric. It has to be electrically neutral. So what happens is you also have equal amount of negative charges also induced. Okay, so you will have positive and negative charges on. So create this kind of positive and negative charges close by, because the charges are not mobile. So you will create another set of such a positive, and so something like this. So you create these positive and charges, negative charges, so on. So let me just draw it here. And this induced charges is because why these induced charges are there? Because the dielectric does not have any free or mobile charges, and that's why you induce the charges within the dielectric itself everywhere. Okay, so it is for conductor you have only on the surface, but for the dielectric you create it within the volume itself. Okay, and this gives rise to or known as, so this is, you can think of you like creating the small dipoles here. So what is a dipole? Dipole is basically a positive and negative charge separated by certain distance. So you have created a dipole, and these dipoles, tiny dipoles, will align within the dielectric so that they can so when we say the capacitance is increasing, so capacitance, we say it, so we defined as Q by V. So capacitance is increasing means V has to decrease. Okay, so V has to decrease. So we have the same number of charges on the conductor. Okay, so Q, the charge stored is the same. So capacitance is increasing means this potential has to decrease. So, and potential is, there is also a relation between your potential and electric field, which is directly proportional. Okay, so or we write E, said it is minus V by D. So that means your electric field has to reduce or decrease. So when we have introduced the dielectric, so electric field has to decrease, potential has to decrease, electric field has to decrease. And how the electric field will decrease? If we have some other electric field other than that is produced due to the charges on the conductor. Okay, so due to the charges on the conductor, you have some electric field. Now there will be an additional electric field due to dielectrics, which is opposite to this E induced, or let's say I write it here. So this is your E induced. So which is opposite to the electric field that is produced earlier, so that the total electric field will decrease and that will increase the capacitance. And how this electric field is produced? This electric field is produced due to this separation of charges, positive and negative charges within the dielectric. And why it is possible? Because these charges are not mobile, or these are all localized within the volume. And this kind of situation is what we call as a polarization. Polarization of the dielectric. Sorry. And this polarization is like it has to happen, okay, irrespective of what kind of so for any dielectric material, so once you apply a electric field immediately, so there will be a separation of charges that will create this kind of dipoles, and eventually that will relate or lead to a polarization of the dielectric, which is a very contrasting situation compared to a conductor. So based on this polarization or the dipole moment that we have created, So it can be done in different ways. Based on that, so the dielectric material has been divided into two different categories. So one is known as a non-polar dielectrics, and another is polar dielectrics. And what is the difference? So in non-polar case, you have a induced dipole moment, and in polar molecule you have a permanent dipole moment. So what is a dipole moment? So dipole, this is what we are saying, electric dipole moment. Okay. So in magnetic also, in magnetic materials also you have dipole moment, which is magnetic dipole moment. So here we have created like a dipole moment is, so a negative and positive charge, so minus q plus q, separated by a distance d. So the dipole moment you will define as q into d. Okay. So simply this is your dipole moment. So irrespective of whether it is a polar or non-polar material, so you will have either a induced dipole moment or a permanent dipole moment. So if you have a non-polar dielectric induced, so the polarization or the dipole will be induced along the applied electric field. Now, if you have already a dipole moment, permanent dipole moment, so that dipole moment will align along the electric field, and this is what that happens within the dielectric when you are applying an external electric field. Now, when we talk of this induced dipole moment, so this is interesting. Why? Because this will happen in any material. Okay, so this induced dipole moment. What is the origin of this? So you can think of that I have a nucleus which is positive charge, and I have electron which is orbiting around it. Now, when we and we assume that this electron are kind of distributed symmetrically, or the charge distribution of electron, it's symmetric around this positive charge, which we can say this is at the origin. And now it may be one electron or many electrons, but if you look at their charge center, so due to the spherical symmetry, so the positive charge center and positive charge center and negative charge center, they are exactly at origin. So they coincide. So that's why you don't have any dipole, induced dipole. But if you apply an electric field, so what would happen? So if I apply electric field, so what would happen? That the positive charges will move a little bit in the direction of electric field. Okay, so let me draw this situation. So there will be some asymmetry that will arise due to, so this is my positive charge center and this is my negative charge center, and a distance, there will be a distance between a positive charge center, basically the nucleus, and the electron, or the charge distribution due to your negative charges, that is due to electron. So a separation occurs, which leads to a dipole moment QD, and also it corresponds to a, which is proportional to the electric field. Okay, so this induced dipole will be proportional to electric field. And what will be this proportionality constant? That is known as alpha E. Alpha is the proportionality constant here, so which is known as atomic polarizability. So this is the atomic polarization. The atom basically is getting polarized due to the electric. So this is a linear relation, as you can see here. But if you apply a very strong electric field, so this can become quadratic, or even higher order terms might appear. But in most cases that we encounter in our life, so electric field, the dipole moment that is induced is typically linear to the electric field that is applied. So this is the induced dipole. So you can calculate what would be this induced value of alpha, because we know you can calculate the electric field. Okay, so we have a charge distribution, and you can do a very simple classical calculation for that. And in case of a polar materials, we have already a dipole moment. So this is a spontaneous dipole moment, electric dipole moment that has formed, and you don't need to apply electric field to create that dipole moment. So why that happens? So if I talk of a polar dielectric, so example is water, H2O. So I have oxygen. Sorry, I put here. So I have, let's say, a oxygen here and hydrogen, H2O. And due to this electron pair, extra electron on the oxygen, so I will have a negative charge here. I have positive charge here, and that gives rise to a dipole moment, which is basically a permanent. This is a permanent dipole moment. So because the nature of the molecule itself, okay, so you don't have to apply electric field to get a dipole moment. Here, the dipole moment exists naturally because of the arrangement of the water molecule in this case, and that gives rise to. So, for example, you can also think of HCl. Okay, so these are some of the polar molecules. Okay, and so what would happen to this dipole in an electric field? So depending on the direction of the electric field, so the dipole, let's say the dipole moment is pointing in this direction, and I'm applying an electric field in this direction. So this dipole moment will try to rotate and get aligned along the electric field. So it will align along the electric field. So this is what a permanent dipole moment will do, or a polar molecule will do. So on this basis, so whatever may be the material, so there will be a dipole moment. Either the dipole moment will be induced due to the electric field, or this dipole moment which exists, so it will get aligned to the applied electric field. And this situation, what we say, is known as a polarization of the dielectric metal. And so one you can define the polarization. So this is again a vector quantity as well. So this is the number of electric dipole per unit volume, so total volume of the material. And now, as we said, the electric field is now different within the dielectric. This is due to this induced charges or permanent dipole. So whatever may be the reason. And this polarization, which is nothing but it is kind of the total number of dipoles per unit volume. So this is also will be, since your dipole moment is proportional to electric field. So polarization I'm writing as a capital P, okay, so not a small p. And this is also proportional to the electric field. And this proportionality constant has this kind of form. Okay, so chi epsilon naught E, simply chi. So this is known as your electric susceptibility. So this is how the polarization will vary depending on the susceptibility of the material. This electric field will vary. And so the chi will be related to your this is side R. Okay. So chi normally also you define as your relative permittivity. Okay, so this is your electric susceptibility, and these kind of materials are also known as linear dielectrics. Okay, so what will be the polarization, the potential or the electric field due to in presence of dielectric? So they will also very similar to what we have seen earlier for electric, for normal conductor case. But only thing what we have is, in addition to these, in conductor we have free charges. So here we have these charges which are immobile or bound charges. Okay, so in dielectrics, so we have something known as a bound charges. And as we said, the bound, why we are calling it bound charges, because they the charges can only move locally, so only few angstrom they can move. So within the atom, so the charge can only move. But in conductor, the charges can move far away anywhere. Okay, so that's why we are calling them as bound charges. And this bound charge depends on what is the polarization of the material. Okay. So this so these bound charges, so you has the form. So we say this is so dielectrics will have bound charges, and these bound charges we can define as a bound charge density, which will be equal to the divergence or del dot P, the polarization. So minus negative of del dot P. Okay. So this is your bound charges. And similarly, you also have these bound charges are basically within the volume of your dielectric. Okay. So which are due to this rearrangement of electrons and positive charges within the atom. And similarly, you will also have some surface charges as well on the dielectric, similar to what you have in case of conductors. So in conductors, you only have surface charges. But in case of dielectric, you have both bound charges within the volume and also some surface charges. That is as a sigma B. So the B, again we are saying to distinguish it from the conductor. So in case of conductor, you simply write it as sigma or sigma F or sigma 3, for example. But in case of dielectrics, we are writing as a sigma B. So which also depends on the polarization and this unit vector, which is perpendicular to the surface. So this n cap is unit vector perpendicular to surface. So you have two kinds of charges that appears in dielectrics in presence of electric field. So what the electric field does, it polarizes the dielectric. So the polarization means you are rearranging the charges within the dielectric, and due to this rearrangement, you have either a bound charge or a free charge. A bound surface, bound volume charge, or a bound surface charge. And the bound volume charge will be given by this relation del dot P. So this is a divergence of polarization. And this is just simply the component of P that is perpendicular to the surface. And these two, both the charges will contribute to the total electric field or total potential within the material. Okay. And so how this is going to affect the Gauss's law or the first law of the Maxwell's equation. So when you look at first Maxwell's equation, we said this is del dot E by rho by epsilon naught, which is mostly correct for free space or for, let's say, for conductors. Now, what is rho in case of dielectric? So in case of dielectric, so rho, you can have the free charges plus your bound charges. So these bound charges are due to the dielectrics. So free charges can be any charge that exists within the space where you are trying to find out E. Okay. I mean, if you say there are no charges, so rho F will be 0. But rho B cannot be 0 because there will be always some induced dipole or some permanent dipole depending on which material you are talking about, polar or non-polar. So you will always have some bound charges. And then what would be the form of your Maxwell's equation? So we said del dot E is equal to rho by epsilon naught, so which we write as two separate charges. So the free charges, which due to the free charges that if that exist, and the bound charges that appear due to the polarization of the dielectric. So which we will write as rho F plus epsilon and rho B, which is of this form, minus del dot P. So we are just simply substituting that here. And now we can write down this equation in a simpler or a different form. So I will take the divergence term to the left-hand side. So this is P by epsilon naught, rho F by epsilon. And this, or I can simply write now epsilon naught E plus P, and I will cancel out the epsilon naught from the denominator. So both sides, I'm just multiplying by epsilon naught on both sides. So this cancels out. So I have this expression, and which in dielectrics we write as a vector D, which we define as a displacement vector. Okay. So this is the electric displacement vector D, which has the electric field the normal electric field that we have described so far. In addition to that, so this vector has, you have to add the polarization of the dielectric material and get the total. This is a vector addition, vector sum, and then you get an electric displacement vector. And now the Gauss's law is modified, and what we are writing as del dot D is equal to rho F. Okay, so rho F is the free charges that that exist within within that volume or space. So again, if you want to write down in an integral form, so here again you use the divergence theorem, and what you will calculate this electric displacement vector D, which will be the Q enclosed. And these charges are the free charges we are talking about, not the bound charges. Or these are the free charges that exist. So this way you can calculate or use the Gauss's law in dielectrics. So which is similar to your earlier expression where we said del E is rho by epsilon naught, or E dot ds is equal to Q enclosed. So here we did not, in this case, we did not bother about free or bound charges, but in case of dielectric, we have to take care of the bound charges which appear due to this electric field which polarizes the dielectric material. And that's why it is not easy. So for dielectrics, it is not easy to find out what is the electric field. So let's say when you apply the Gauss's law, you can find out this D, electric displacement vector, easily. But in order to know the electric field, calculate electric field, you need to know what is the polarization. And polarization is not that easy to calculate or find out in dielectrics. Okay, so that's why we are using a new vector quantity D, so that we can calculate the find out what is the electric displacement vector, which is the equivalent of the electric field in case of conductors or in free space. Okay, so whenever we talk of dielectric, so we will always refer to this electric displacement vector, which is similar to the electric field, but it has a term which depends on polarization of the material, and the polarization of the material can be different depending on in which direction electric field is applied, what kind of material is taken, and so on. So there is no simple answer to find out what is the displacement vector. But if you take a linear dielectric material, so we can write, so there is a linear relation between polarization and electric field. So we said the polarization will be equal to the susceptibility into the permittivity and the electric field. So if we substitute that, so D will be equal to epsilon naught 1 plus chi, or let me just write it down. It will be epsilon naught E plus chi, epsilon naught E. So we take epsilon naught and E, the common factor out. So it is equal to E. So which sometimes also written as epsilon. Okay, so D is equal to your epsilon naught E. So which is the dielectric permittivity, or the simply just called the permittivity of your dielectric material. And you can define the relative permittivity as epsilon R, that is E equal to 1 plus chi, which is also known as the dielectric constant of the So this is for a linear dielectric, but many times this relation can change depending on what is the electric field you are applying. But nevertheless, so we need to introduce a new vector quantity which takes into account the electric field as well as the polarization, and this polarization which arises due to the bound charges within the dielectric, and this is how the equation is modified in case of dielectric materials. Okay. So I will stop here. So in the book, you will find many more examples of how you can solve this or on the online material. So you will find out some examples of that. So please try to solve those examples. So what I would do tomorrow is we will complete magnetostatics, and then I will move into magneto or electrodynamics, because they are pretty much kind of a related things. And also one of the most important aspect in physics when we talk of electromagnetic theory, why or what uh, actually what was the necessity to write, like why there was a necessity by Maxwell to write all those four equations in that form, and how uh, because once we know those equations, so we will use that to, I mean, basically that is used in every aspect of our life, as I said. So we talk of reflection, refraction, any communication that we are doing, electrical communication or electronic, like any data transfer that you are doing, uh, like internet that we are getting through optical fiber. So these are all electrical signals that obey this Maxwell's equation. Okay, so starting from your sunlight, how the reflection, refraction that is occurring, scattering that is occurring, up to our transfer of this high-speed data. So everything is kind of governed by this Maxwell's equation. So we will see how that from static to dynamics, how that transition happens. Okay, any question?
Sir, can you define electric susceptibility once again, sir?
Electric susceptibility is defined. So this is defined only in case of linear dielectric materials. So what I mean by a linear dielectric material, so the polarization is proportional to E. Okay, so this is always linear. Why we are saying linear? Because it is just the proportionality is E to the power 1. Okay, so that is why we are calling it a linear. There is materials where polarization can depend on E square or e to the power 4 or higher order terms, but we are, so those are known as non-linear materials, a non-linear dielectrics, but this is a linear dielectric. So the polarization is proportional to the electric field, and this proportionality constant we are saying is depends on the susceptibility and the free space permittivity. So susceptibility you can think of as like any response that you get due to an external stimulus. Okay, so I am applying some external electric field, or it can be a magnetic field. So how the medium responds to that external electric field. Okay, so whatever is the stimulus that I am giving, so how that is responding, so that is basically the susceptibility. So susceptibility will be low for a material if it doesn't react to anything. You are applying electric field and it does not react too much, so the susceptibility will be low. And if a material reacts immediately to a small electric field event, so that will have a high susceptibility. So this is what this susceptibility actually means in this case. So it also has a similar understanding in magnetism as well. So exactly the same. So if you are applying a magnetic field, so you will induce a magnetization M. Okay. So electric dipole moment you will induce, and you will have a magnetization. So similar to a polarization, you have a magnetization, and also you can define a magnetic susceptibility as well. Okay.
Okay, sir. Okay.
Okay. Any other question? Okay, if not, so already the time is tough. So I will try to post at least these materials I will post, and so we will meet tomorrow and continue our discussion. Thank you.
Thank you, sir.
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 Thank you, sir.